Okay, first couple of questions. Did the video recordings and homework help? Right? They were okay, right? They helped. I hope you used them the way I intended them, that you tried the homework first. And then if you were struggling with those problems that you had problems with, you could go there and like take a look at them and see if that would help. Okay, so rather than just look at them and get the answer and stuff. I think next time I'll probably do the same thing, except maybe not work it to the final conclusions. There's 4 sheets here. Let me make one, keep one for myself. There's each one of these handouts is 2 pages, and I grabbed an extra page there. No, it's got to be in the. It's off. Yeah, right. Probably goes with that. Okay, there are 4 pages, and first page is a summary of some of the values or variables that we're going to talk about tonight for radiation. Tables, kind of conversions and definitions and stuff like that. And the other pages are problems that we're going to work through as we go through the slides here. Okay? So I'm going to put together a homework that's kind of very similar to this, but these we're going to do in class. At least we're going to do as many as we can get to anyway. Okay. How many of you haven't started the homework yet? Well, let me ask you that the other way around, because you may be more willing to admit it. How many of you have at least done the homework once? I mean, the exam once. Yeah, the exam once. I got about a third of the class has done the exam at least once. At least, and some people have already finished it. One person got 100 on the first try. Right. So just to let you know, it's attainable. Okay. And for those of you who haven't opened the exam, they are probably, the questions are not as difficult as the homework questions. Okay, they're reasonable, I think. Okay, so I think that should encourage a bit. Plus, you'll have a chance to take it as once you see it's 4 pages long. Maybe I should have numbered the pages or found somebody in one of these offices that has a stapler. But the first page is the tables and the definitions, and the next 2 pages are problems 1 through 7. So you should be able to figure this where the pages are. That you have the right 2 pages by the problem numbers. So at any rate, the only thing you have to be careful about, you have 2 attempts to take the exam. Your final grade is an average of the 2 attempts. When you finish the first attempt, it will grade it automatically, and you'll be able to see which responses that you had that are incorrect. Right? Won't tell you the answers, but it'll tell you which ones you got wrong. Then when you do the second exam, you don't have to do the second exam right away. You got until the end to do the second exam. But when you do the second exam, you might want to write down your answers from the first one, because we'll start with a blank slate. So if you don't want to redo the ones that you got right, there's no way for me to just give you the ones you got wrong, let you do them again. So you might want to write down your answers. With one caveat, there is one of the questions is matching, A, B, C, D, E, F, and you got to match it with 1, 2, 3, 4, 5, the right A6 or something like that. That one may, sometimes when you set up on Blackboard, it randomizes. So the first time you take the exam, the correct answer might be A6, and the second time you take the exam, they may be A4 or something like that. So that one will not random. That one will tell you. That one may not be exactly the same as the first time you took the exam, but all the other questions be exactly the same. So good luck on that. Somebody took about 20 questions, I guess. Of those 20 questions, I would say about 10 are short problems. 8 to 10 are short problems. The rest are kind of multiple choice and stuff like that. Okay. I think you get 1 point for answering true or false to whether you did the exam on your own or not. You got outside help. So the answer to that is true. You did it on yourself. Did it yourself, just so you know. I'll wait for you guys to settle in. Okay, let me just repeat for you guys that just came in. You have two tries at the exam. You have to be done with both tries by end of the day on Sunday. That means midnight on Sunday. It's going to turn into a pumpkin, right? You're going to be done. After you take the first exam, after you take it the first time, you will be able to see by going to the grade section and clicking on your grade, you'll be able to see which problems that you got wrong. It won't give you the right answers. You'll have to go back, take the exam a second time. Doesn't have to be immediately, just before Sunday night. And you'll be able to take the exam a second time. The exam will be blank. You get a new copy of the exam. They'll be blank with the same questions. You probably should write down your answers from the first time you took it, so you don't have to bother with the ones you got right again. With one caveat, there's a matching in there, like A7, B3, and so on and so forth. You have to match up 2 items in 2 columns. That one may not be exactly the same as the first time you took it. It may randomize. So just be careful with that question. Okay, so let's get started on tonight. We're talking about radiation now. So our second major topic. We have some other topics we're going to be talking about, like ergonomics and some other stuff that are not really covered in any other courses here. So we get to freelance a little bit as we get closer to the end of the semester. But the first 2 parts of the semester are generally noise, thermal stress, and then radiation. So as far as the exams are concerned, they're going to be non-cumulative. We're done. As soon as you get done with that exam on noise and thermal stress, we're not going to have to go look back at it for the next exam and so on and so forth. So you don't have to worry about that being an issue. Okay. Anybody work in radiation here? Anybody work in a hospital or something like that? What do you do?
No, I'm in the
Uh-huh. What kind of work do you do that you have to do monitoring? Okay. Oh, okay. I got you. All right. So XRF, you're not expecting too much of an exposure. So you wear monitors? You got the guys that do lead wear monitors when they're doing the XRF work?
Usually you don't have to, but we have
Oh, okay. Okay, good. All right. Very interesting. All right. Where do you wear the? I guess you wear the monitor on your collar or something like that. I mean, that seems like the least likely part of your body to be exposed, right?
Yeah, they have wrist monitors.
Okay. Yeah. Your hands, I guess. Yeah. Yeah. All right. Well, that makes sense. All right. Okay. So anyway, what are we going to do tonight? We're going to try and understand the basic physics and sources of ionizing radiation. Identify health effects. That's really kind of maybe the next section a little bit more. Be able to make relevant calculations. Definitely, we're going to get started on that tonight. Understand applicable occupational exposure standards for radiation exposure. That's really more next session also. Determine appropriate controls for reducing ionizing radiation exposure, also next session. But a lot of this stuff we're going to cover tonight. Okay, so understanding basic physics and sources of ionizing radiation. One of the issues here that makes this a little bit difficult to do is that, let me just, I'm going to have to wait till we get to that slide, so I'm not going to jump to it. One of the issues that we have is that the nature of the various kinds of radiation that we have to monitor or be concerned about exposure to can be particles. It could be electromagnetic radiation. It could be something that has a dual property, photons, particles, and sometimes electromagnetic radiation. Sometimes of the particles, there are many different particles, have different energy levels, they have different speeds they travel at, they have different mass, and so on and so forth. Then we're also looking at electromagnetic radiation and different wavelengths for that electromagnetic radiation, different energy levels. So the problem is it really isn't just one thing that we're measuring. So things can get a little confusing in terms of what kind of units, what kind of values that you're going to record for these different kind of measurements, how you're going to relate them to each other, how are you going to relate all of these different kinds of particles and waves and so on and so forth to a person's exposure to these things, how are you going to quantify the exposure, and how are you going to quantify the health effects. So every one of these steps along the way has pitfalls to it and can be a little bit confusing. So we're going to try and organize this as best we can. And if you look on the first page of this, as we're going through this, I think I got this pretty much in order in terms of like the different kinds of values, like Curie's and Becquerels. How do you pronounce that? Do you pronounce that Becquerels, or do you not know? Have you not? BEQ. Well, Becquerel, the guy who discovered radioactivity. French. It's French. Anybody know how to pronounce that? Huh? What's? Yeah, the second line there. There you go. How do you pronounce that? Becquerel? Becquerel. Okay, Becquerel. Okay, guy that discovered radiation, basically. Okay, and he's that and curie is a basic way of measuring radiation. It's disintegrations per second, decay per second, or disintegration per second, conversions per second. Problem is that there's all kinds of different kinds of radioactive particles and waves and so on and so forth. So while that's an interesting scientific original definition of it, it really doesn't do us too much good in terms of like our exposure. So we're going to have to look at some other stuff here as well. So you see some of, as we go through this is more or less in the order that we're going to be going through these different measurements and values. Okay, so some basics. This semester we're going to be talking about ionizing and non-ionizing radiation. The difference is that the energy level of ionizing radiation is sufficient to knock electrons off of molecules. So those molecules become ions. So in a sense, that's really just the key. Is there enough energy to knock an electron free from a molecule and ionize it? Okay, non-ionizing energies and radiation we're going to be talking about later on in the semester, and that involves sunlight and microwaves and so on and so forth. We'll be discussing that stuff as well, and maybe even bring some equipment in here and do some measurements and so on. Okay, electromagnetic spectrum. Before that blue line in the but basically what you're looking at here is the electromagnetic energy, okay, which is basically energy moving through space. Doesn't need a medium, can move through a vacuum, can move through walls, metals, and so on and so forth. Microwave radiation, obviously, we got our phones, we make phone calls in the basement and stuff like that, so it gets through a lot of materials. But that blue line represents the point at which the electromagnetic spectrum, the energy of the waves in that spectrum, are sufficient to start being able to knock electrons off of molecules and go from a transition of non-ionizing radiation into ionizing radiation. You can see in that spectrum, you can see microwaves, infrared energy, visible light, ultraviolet light, and then crossing over into X-rays and so on and so forth. So right kind of in that intersection there, ultraviolet light, UV light, and stuff like that. You go to the beach. What do you slather all over yourself nowadays at the beach? Suntan lotion, right? And you're protecting yourself from what kind of radiation there, right? Yeah, ultraviolet radiation, right? Primarily because it's kind of like a crossover, right? It's really at the point where some of those, I think UVB or UVA, the different wavelengths, some of those have enough energy to start causing some molecular damage in your DNA. So it's really starting to cross over to the point where you're going from visible light into something that is on the borderline of ionizing radiation. Okay, so atoms. This is an old view of that. This idea of orbits, like electrons with orbits around a nucleus and stuff like that. I think that's kind of like an old view of what an atom is structured like. I think more nowadays I kind of look at it more as kind of like this electron cloud that's kind of diffuse and not well defined. But this is the traditional old view of what a molecule looks like, a nucleus and the electrons orbiting around it in some fashion. Okay, atomic symbols. First thing we're going to do is we're going to show you a format for how we're going to describe the molecular weight and the atomic number of an atom, of an element, of an atom, and then we're going to automatically abandon that and show it to you in a different form. Right. So right here, what we're seeing is that the atomic number is 6. It has 6 protons in the nucleus, 6 electrons in its cloud or orbiting it, and its molecular weight is 12. So the 12 and 6, that means you have 6 particles that don't have a charge, so then they would be neutrons, right? So you have 6 protons, 6 neutrons, and that's your atom of carbon. Okay, so In 1869, Dmitry Mendeleev started the development of the periodic table. What he did was he calculated the molecular weight, really the combination, the atomic mass, the combination of the protons and the neutrons. The molecular weight, he tried to determine the molecular weight of these materials, of these different elements, and he tried to organize them by molecular weight and by properties. What kind of properties they had, which ones were metals, which ones were, were non-reactive, and so on and so forth. And he put together the periodic table. He was so good at it that, in fact, he was able to leave spaces for elements that they weren't aware existed at the time, right? And that would get filled in later on. Okay, there you are with, this is happy birthday. It's 150 years since the creation of the periodic table. Okay, so here's a typical periodic table. Okay, so again, we have the atomic weight, the atomic number, and the molecular weight. So we kind of change that around a little bit. But you can see carbon up here is, of course, 6, and the molecular weight is 12.011. So the deal here is that it's a little bit more complicated than that, because obviously it's not exactly 12. So something else going on there between just the protons and the neutrons and binding energy and electrons and so on and so forth. But pretty much that's what we're dealing with. The other issue is that for many of these elements, there are isotopes where the element itself is defined by the number of protons, number of positive charges, but it can have a different number of neutrons. So the molecular weight of these various materials are different. So some of these isotopes are radioactive, meaning they decay, they fall apart, decay, break up, and so on and so forth, release neutrons. Some of them are not. Some of them are stable. Among the ones that are higher molecular weight, they tend to be radioactive materials. So you've heard about uranium-238, and 235, and 234, plutonium, and so on and so forth. A lot of those materials, those isotopes, are important. Like right now, we're very concerned about people. Uranium-235 is relatively rare. It's much rarer than uranium-238 in the environment. Plutonium is almost non-existent in the environment. But those materials are fissionable materials that you can make bombs out of. You can use them in reactors because they're easily fissionable, or you can make bombs out of them if you refine them enough. Right, so the idea of refining, changing one isotope into another is really important kind of stuff that you wind up dealing with, and also they become the sources of some of the radioactive materials that we're concerned about in terms of waste from these different processes and so on. Okay, Antoine Becquerel, close enough. Okay, good. You're not helping me that much here, son. Okay. He first discovered radioactivity, first discovered this idea of atoms decaying, right? And he wound up sharing the Nobel Prize with Pierre and Marie Curie. Okay, so unstable atoms, the nucleus has too much energy or mass. It eventually releases particles, mass given off with energy of motion, photons of energy, electromagnetic radiation. And again, we're calling it ionizing radiation because that particle that's given off, or that electromagnetic radiation that's given off, is capable of removing electrons from other atoms. Okay. Okay, so problems describing and quantifying radiation. It's not just one thing. We got different kinds of particles, alpha, beta, neutrons. We got different kinds of electromagnetic radiation, photons like light, X-rays, gamma rays. What's the difference between an X-ray and a gamma ray, by the way? Anybody want to hazard a guess? What's that? Yeah, the gamma ray is higher energy. But besides that, X-rays are usually man-made. They're man-produced. They come from some device or some process that we're working with, right? And usually they're lower energy than gamma rays. Gamma rays very frequently have a natural source, like electromagnetic decay, molecular decay being released as you have molecules decay, atoms decaying, or I think also cosmic rays have a gamma ray component as well. Okay, the energy of all these things can vary. You can have gamma, X-rays, gamma rays, a continuum, so different levels of energy within that continuum. The particles themselves, different speeds, different energy levels, and so on and so forth, right? Each one can vary quite a bit. And then on top of that, the way this energy from these different things, these different items that are radiation, that we call radiation, the way that they're absorbed by organisms, like humans, for instance, that can vary quite a bit in terms of like how much of the energy is absorbed, what kind of damage it can do, and so on and so forth. So we have so many different variables in terms of how we going to quantify radiation, how we're going to describe the health effects of a certain level of exposure. Okay, so let's take a look at these guys. Alpha particles, they're basically like the bowling balls of these particles. They're large. They're basically a helium nucleus, two protons, two neutrons. Their travel distance is relatively short in air, and they only travel a short distance through air, and also they won't go through most materials. They won't go through your skin. They won't go through paper, and so on and so forth. Their main hazard is if it gets into your body. Where's the most likely source of alpha particles getting into your body? You want to hazard a guess? Radon. Bingo. Who said that? Good. Great. Okay. No wonder you're in charge of the radiation. So yeah, radon. How does that happen? Right. Yeah. Exactly. For radium decaying into radon, decaying into a whole series of particles below that. So radon has a relatively short half-life. Radium in soil, trace amounts of radium in the soil, which is a solid. Decay, you get radon gas, which is a gas. It's in the soil and a gas. And if you take a big giant cup and turn it upside down over the soil, that gas that's in that soil can enter and accumulate in that big giant cup. We call those houses nowadays. Right, that big giant cup, you dig a hole, you cover the hole, and now you have a radon capture device, right? Especially in the wintertime, because in the wintertime, what are you doing? You're taking air from the basement, you're mixing it with gas, you lighten it up, and you're sucking air out up the chimney, so you put the basement under negative pressure, so you're sucking those radon gases in the soil into the house. If you don't have radon gases in the soil, you don't have any problem. But we have a geological formation here in the Northeast called the Redding Prom, which goes through Pennsylvania and New York up into New England. And that is an area that you're not going to go mining for radium in that area, but it's an area that has a little bit more radium in the soil, dispersed in the soil, than most other places do. So we do have an issue with some homes. Radon is the second largest cause of lung cancer after smoking. By the way, smoking. What about smoking? What causes cancer with smoking? Anybody has a guess? What's in smoking that causes cancer? What's that? Carbon, tar, carbon, nicotine. Well, maybe not nicotine, but it's got other effects and stuff like that, right? Yeah, you would think like, the various tars and other materials. When you examine epidemiological studies that involve, cigarettes with high tar or low tar and stuff like that, turns out that there's a small effect in terms of the amount of tar that's present, but it's not that gigantic. The effect's not that big. However, most cigarettes contain a significant amount of, when I say significant amount, tiny, but a measurable amount of radiation, alpha particles being released from the smoke. So that smoke, and then mostly that is from materials that they fertilize the tobacco fields with, or that's naturally occurring in the soil, phosphorus and stuff like that, that's naturally occurring in the soil. So you have another source of cigarettes. In fact, one of the reasons why they cause lung cancer, part of the reason they cause lung cancer, may have something to do with radioactive material, alpha particles being released in the smoke that you're inhaling. So the radon goes into the house, it decays. The radium has a long half-life, but it's sitting in the ground decaying forever. So it's easy for you to suck it into the house. Radon has a relatively short half-life, I think days or something like that. It sits in the basement. When it decays through a series of other particles, one material decays, radon decays, one material decays into the next and the next, and those are called radon daughters, right? That sequence of particles that are created as they release, mostly alpha particles, as they release the energy in alpha particles. So those radon daughters, they have a relatively short half-life, and they're solids. So here you have a gas molecule floating around in the air, turns into a solid. It's got to connect itself. In other words, it's going to do now. It's going to fall out. But it's such a tiny particle that chances are it's not going to fall out of the air very quickly. Most likely it's going to attach itself to a dust particle or some other material in the air, and you're going to wind up breathing it. Gets into your lungs. It's got a short half-life. It's likely to release an alpha particle inside your lungs. So those alpha particles, where are they hazards? They're hazards when they're inside your body, when you ingest them, when you breathe them in, and so on and so forth. So that's mainly where we're concerned about alpha particles. Beta particles, also short, relatively, they're more energetic, faster, short, also similarly done, relatively short travel distances through the air. They are a little bit more penetrating. They'll penetrate skin to some degree, and because they'll penetrate skin to some degree, they are both external and internal hazards. Shielding material, plastic, wood, aluminum, paper is good enough for alpha particles. Notice it doesn't say anything about steel and concrete for those materials, right? We're going to find out later on that beta particles, which are electrons, we're going to find out later on that there's an issue when you try and block or shield using certain kinds of materials with electrons. With certain kinds of materials, you can cause a little bit of a problem. We're going to figure that out later on. Gamma rays or X-rays, again, X-rays generally you're referring to man-made high energy electromagnetic waves. They are, when they say infinite, they don't really mean infinite. They're infinite in traveling through, let's say, a vacuum or something like that. But they are slowed down by various materials, and you can do some shielding with them. They're deep penetrating. They'll go through your body. If they're energetic enough, they'll go through your body completely. And they're, of course, an internal hazard as well. So you get X-rays, you know that they go through your body. Neutrons can vary based on the energy level of the neutrons. They typically are deep penetrating, and again, they're internal and external, but they have special needs in terms of materials that will slow them down or interfere with their movement. So you can see that there's a little bit of unusual shielding material when you're dealing with neutrons. Neutrons are one of the elements that is common, that is used to maintain fission in a reactor, right? So you guys have probably heard that in reactors, they very frequently immerse the core in water, right? What kind of water? Right? They use heavy water, right? Deuterium or heavy water in those. But again, that's because it helps them control the movement of neutrons. Okay, alpha decay, radon to polonium. That's the first radon daughter, and so on and so forth. Okay, eventually, what do all these radioactive materials decay into? Right? What do you think? Right? If they keep losing electrons and protons and neutrons and so on, they eventually all decay into lead. Some of them, take longer than the Earth has been around to decay into lead. Some of them take 500 million years, and so on and so forth. But eventually, they all decay into lead. Alpha particles plus 2 charges interact with the human tissue, travel only a short distance. Beta radiation, again, they're basically electrons. Doesn't penetrate, can travel over a few inches to 10 feet in air. Shield it with these various materials. Notice certain kinds of emergency vehicles. If you're having a problem and you can hide behind your car, basically, that means. Okay, so shielding beta radiation. There's a little bit of a problem with shielding beta radiation, and that is particularly a higher energy beta radiation, high-speed electrons. When they hit certain materials, they slow down and they lose energy in that material, and they release energy from that material in the form that energy that they give up is released in the form of X-rays, right? So if you wanted to make an X-ray tube, right, what would you do? What's an easy way to make an X-ray tube now that you know that? You take a material that will slow down electrons and send off X-rays instead, and you just beam a cathode ray at it, right? Like electrons at, like your TV, the old TVs. And I'm dating myself when I say your TV uses the cathode ray tube, right? They don't do that anymore. But in the old days, the old TVs had a cathode ray tube. They beam an electron beam at phosphorus, and it would glow, as you and trace lines as you faster than your persistence of vision, and you would see a picture on that device. In this case, they're beaming them at material that instead of releasing visible light will release X-rays. So you can make X-ray tubes from that. In fact, you can probably look it up, but your XRF probably has a device like that. Uses your old school uses CAD. So his device is XRF, which is old school, and that's why you have to do all the monitoring. Yeah.
The newest device now.
Oh, no kidding. Because I thought most of them use X-ray tubes now.
No, for in order to use it for paint, like certified.
Yeah. Oh, no kidding. Okay, I didn't realize that. But the ones with X-ray tubes can still work for lead, right?
Yeah, but they're not certified.
Oh, okay. So what is that? I mean, they're just lagging behind the technology, or?
It's very expensive.
Yeah. Okay, so they just give you the one. So they have a little pellet of cadmium in that, radioactive cobalt, rather, right?
Yeah.
Radioactive cobalt in that device, which gives off gamma rays. And he's got a little window in there. And he's got a little safety device in there. So when he pushes this device against the wall, right, and pulls the trigger, it actually opens that little window and exposes the shield. It takes away the shielding that's keeping those X-rays from getting out of that machine, right? So yeah, no wonder you're doing all that monitoring. Okay, and then and now the X-ray tubes, they deteriorate over time. Does the radioactive cobalt have to be replaced too?
Yeah.
Okay. Okay, great, because it has a half-life, right? So it loses energy. So he needs a certain amount of energy to excite the metal atoms or ions in the paint in the wall, so that they can send back some other radiation that he can detect and see what's in there. But when they get when that cobalt, when the energy of the X-rays or the number of gamma rays, the amount of the intensity and the energy of those gamma rays that diminishes, what does he want? What winds up happening?
The first time it takes a longer.
Yeah, exactly. So your instrument's going to keep it collecting data until it has enough data and give you a result. And like what happens is now what used to take 10 seconds now is 3 minutes. And finally you decide it's not worth keeping anymore. And what do? Send it in and the manufacturer replaces it. Yeah. Okay. Right. That's called a Bremsstrahlung. That has I think, breaking rays. That's what that means. Okay, so that's how we generally generate X-rays or gamma rays for various purposes like that instrument and maybe your dentist as well. Although who knows with that, I'm not sure. I'll ask my dentist next time. Okay, high-speed electron, beta radiation. X-ray and gamma radiation is electromagnetic radiation. We know that is kind of like this electromagnetic wave or energy that is in packets like photons. It's very high frequency. When you view it when you measure it as a wave, it's very high frequency. Very short wavelengths. Has enough energy to strip off the orbital electrons. Okay, X-rays have very similar properties, except they're usually emitted from anthropogenic sources, man-made sources. Gamma radiation is typically emitted by the nucleus of an unstable atom, or again, electrons in the material. Okay, neutron radiation, cosmic rays associated with cosmic rays, upper atmosphere. Fission process involves the generation of neutrons that maintain a chain reaction. I think we jumped up on that. uranium, here's uranium breaking up in its nuclear fission, a neutron striking a uranium-235, not 238, 235 nucleus, breaking it up into two smaller atoms and releasing energy and additional neutrons. Each neutron hits that nucleus, releases then 3 neutrons, which then hit others, and hence a chain reaction. And hence, all these neutrons running around, you need a way to control that reaction as well. So you use water, heavy water, and use control rods and so on and so forth. What did they use in Chernobyl instead of water to control the neutrons in that reactor? Anybody know? Well, before the explosion, what were they using? It was a graphite reactor. They were using carbon to control the reaction, to contain the reaction up to that point. Yeah, after that, they weren't using anything that contained it because it blew up. How many of you guys watched the movie, that series Chernobyl on PBS? At least the one guy that's interested in radiation watched it for sure. Okay. All right. Good. At least you know what can go wrong. Hope. Well, up to that point, yeah. I mean, up to that point, what did they keep saying throughout that? Every physicist, every nuclear scientist, that was about it couldn't explode. It was impossible for it to explode. So yeah, learn something every day. Okay, and here's an example of various kinds of shielding. And again, the shielding may be specific to the kind of radiation that you're trying to control. Okay, we got two measurements, two ways of measuring. Well, we have two basic measurements for how active a radioactive process is. One of them, both of them involve just counting the number of disintegrations that you have occurring per second. Okay, that's the becquerel, which is 1 disintegration per second, and 1 becquerel is 1 disintegration per second. As you can imagine, if you have a significant amount of this material, you're talking about a lot of disintegrations going on at the same time. So this other unit is the Curie, which is 37 billion becquerel, so 3.7 times 10 to the 10th. Okay, so disintegrations per second. So typically, you might see levels of radioactivity in an environment measured not in becquerel and not in curies really either, but in like picocuries, right? Like a billionth of a curie, which is like thousands of disintegrations per second. So we're just talking about radon. What's the action level for the level of radiation in a home in terms of picocuries? 4 picocuries per liter, right? So I think what it is, the level of disintegrations in a home, and that action level, I think the EPA kind of correlates that to the risk of developing lung cancer, equivalent to about a pack of cigarettes a day, right? So it's a significant hazard. In other words, every time you get every time you get a release, right, a change in the atom, a release of a particle, a disintegration, a molecule breaking up and releasing something, energy or whatever, every time that happens, it could be a photon, it could be an electron, it could be a neutron, it could be an alpha particle. That's why this is so imprecise. In terms of describing an exposure with this, it really doesn't make much sense, right? I mean, you measure you're with the radon, you're describing as picocuries per liter of air in the environment that per some amount of time, typically, maybe I don't know if it's second or minutes or something like that, but over a period of time. But the understanding there is that almost entirely that's alpha particles, right? So you're dealing, when you have that exposure level, you're dealing with that level, that number of alpha particles. But this could also be used to describe the number of neutrons being released, or the number of photons being released, and so on. So it's really not really precise in terms of the how much you might absorb from that same number of disintegrations per second, if it were beta particles or alpha particles or photons. Or what's that? or how far it's going, and so on and so forth. Yes, just simply a way of counting how much radiation is taking place. Really not very non-specific in terms of energy and speed and effect on organisms, absorbance, and so on and so forth. There's a Geiger counter. Here's we'll talk about it later on. You don't see this in use too much anymore, but it'll measure beta and gamma radiation. Very common instrument. You probably don't see this too much anymore because you're using monitors of various different kinds. You have two. Do you use them for anything? Yeah. Right. Okay. But the release is gamma rays, right? So this will react to gamma rays. Yeah, gamma and X-ray. This will react. So let's talk about Geiger count. As a matter of fact, let me speed up here. I want to show you a video because this is going to be interesting and okay, here. I don't have a speaker with me. Shoot. I wonder if I can't do this. I'm going to try this. Maybe I'll narrate it or something like that. I got to stop the recording while I do this.
This conference will now be recorded.
All the different kinds of measuring devices at one point or another either is a Geiger type device where you're radiating a inert gas to ionize it, and once it ionizes, the electrons cause a cascading effect where you get a whole bunch of these electrons. Whole bunch of these electrons at the same time, so you can hear a click, or you can count how many times you get this discharge. A similar device where you're measuring the conductivity of the gas as it's being exposed to radiation, and devices that use some sort of way to make a material luminesce and then measure how much light you're producing from that luminescence and relate it back to how much radiation and what kind of radiation that was present. There's another one too. Have you ever used in radon testing? Have you ever used a track etch meter? Right. It's a device that, one of the ways that you measure radon is you take an activated charcoal packet, you put it into a basement for 3 days, it absorbs radon gas, and then it goes to a lab, and then they analyze it and tell you how, they evaluate how much radiation is coming off of the thing over a period of time. And they can kind of like calculate back how much radon must have been present in the basement when it was stored there. There's the other kind of things called track etch meters, and they're plastic or film. They're either light or plastic, and you leave them in there for several months, and then they get sent to a lab, which either develops the film or processes the plastic, so they can actually count how many alpha particles went through that material while it was in the basement. So that's a track etch meter. When the first time I ever did radon testing was before the EPA had approved track etch meters, activated charcoal packets, or other methods for measuring radon. It's really pretty new. We actually used a scintillation counter, which was a device that could produce electrons. You could put what you do is it had a little pad where it would take a filter, like a 35 millimeter paper filter. You would go into a basement or into a space that you thought might have radioactive material, particles in the air, dust, and so on and so forth. You take an air sample, just like you would any particulate sample. You take the filter after you have the process of a known amount of air. Take the filter, you stick it into the scintillation counter, you close it up, and the scintillation counter beams it with electrons. What does that do? Actually, I'm wrong. You put it in there, and you wait for the material in there to cause photons to be generated by the material on that pad. And the scintillation counter is enclosed, and you sit there for an hour or something like that while it tries to do a count. Then you would take that number that you get, number of disintegrations per second, right? Becquerels or becquerels in this case, most likely, right? Not that many. And believe it or not, we could find one Russian guy wrote a paper in Russian that we had to have translated on how to convert that into picocurious per liter, right? So we're literally just, using, kind of our wits try and figure out how we might actually be able to measure this. And we wound up not using our wits, but using the wits of some Russian guy that had published a method for doing this. And I think within 6 months, the EPA had a method. So that's the last time we ever did that. So I don't know. They spent a lot of money on this scintillation camera. I don't know whatever happened to it. But at any rate, let me get back to the slide that we were on. Okay, where was I here? Shielding.
So you said you wait for the filter to generate.
Yeah, that must be the way, because it's kind of sitting there for a while. You couldn't irradiate it because you're waiting for it to generate the particles. It was only outside long enough for you to collect the particles that were in the air, the dust in the air, and then you put it into the scintillation counter and waited for an hour.
How long did you leave it out?
In the scintillation counter? In the cassette, well, depends on how much air that we would do. In other words, that was part of the calculation. In other words, the level of precision that you wanted was based on how many liters of air that you sampled. So, yeah, we'd suck air through a filter. I don't remember if it was a paper filter, like 35 milliliter paper filter, or if it was like, we probably used whatever we had, most likely. And I think we also, just to be safe, did field blanks by actually using just the filter itself. Because in case we didn't know if the filters had, we didn't know what we were doing. Basically, is what it was. There was no real procedure for this, so we were just keeping customers happy. Is what it is. You know what that's like, right? Keeping customers happy. Yeah, exactly right. Yeah. They want to test. They insist on testing. How much do you tell them that they don't need to test? And just ventilate the basement. We got to test. Okay, so anyway, so one of the other properties of radioactive material is that when these atoms decay, you don't have them anymore unless they're the thing that they decay into is also radioactive. You don't have that, and perhaps a similar or shorter half-life existence. You don't have that material anymore. So gradually, over time, these radioactive materials decay until they disappear, right? So the problem with that is that, like with a process like this where they're randomly decaying, some of them basically you get less and less and less of it, and you never get, in a practical sense, you never really get to zero. So instead of measuring how long it's going to take to completely decay, you measure how long it takes for half of the material to decay. Doesn't matter if you got a pound of this stuff or ounces of this stuff, the rate at which it decays is the same, so the half-life is the same, no matter how much of the stuff that you have. Whatever you got a gram of it, in 100 million years, you're going to have half a gram. You have a pound of it, in 500,000 years, you're going to have half a pound. So half-life's a practical way to at least be able to describe the rate of decay of the material or how long your cobalt source is going to last in you. It's decaying even when you don't use it. Doesn't matter if you use it or not. It's going to last 2 years, whether you open that window or not, right? So half-life. Okay, so carbon-14, an isotope of carbon, is 5,760 years. So now carbon-14. So carbon-14, for some reason, which I don't understand, anthropologists know that most organic materials start with a certain percentage of the carbon in them being carbon-14. I don't know why that is. I don't know why that occurs that way. But what does that tell you about carbon-14? If you know that its half-life is 5,760 years old, carbon-12 doesn't decay, just stays carbon-12. So if you start out with it's not equal amounts, it's tiny amounts of carbon-14, but assume it's equal amounts. If you start out with equal amounts of carbon-14 and all of a sudden, and carbon-12, all of a sudden the proportion of carbon-14 to carbon-12 is now half of that. Well, half of the carbon-14 must have decayed, right? It's gone. How long did that take? 5,760 years. You can use it to age organic materials, bone and stuff like that, right? You can maybe not bone, not carbon necessarily, but like trees and relics and whatever. What's that? That's a good question. And maybe there must be some carbonous material in them if they're going to use this method to age them. So you need to see that ratio of carbon 14 to carbon 12. Sulfur 35, 3 months. Phosphorus 32, 14 days. Iodine 131, 8 days. Why is iodine important? That's another important element that's released very frequently in nuclear fission. And if they have an accident, some of that gets into the atmosphere. What happens? It's iodine, right? What happens to iodine? Do we need iodine? Iodine is a metabolite. Our bodies need it. Most of it get it from what? Salt, right? By iodized salt. So if you don't eat a lot, what foods? Anybody know what foods iodine is in naturally? Fish or something like that? If you don't eat enough of the foods that have iodine in them, you supplement it, or we casually supplement it by using iodized salt, by usually buying iodized salt. You don't get enough of it, then you get supplements. Most likely, if you look at your supplements, your case, the Flintstone stuff. My case, the geriatric stuff. So if you're looking at stuff, I'll bet you'll see iodine on there somewhere, right? So at any rate.